Hello everyone, in this video I'm going to present our recent research with the title of Hybrid Predictive Rebalancing Control of Perceived Usability in Shared e-Scooter System. Shared e-micromobility systems, or more specifically shared e-scooter systems, appear as a solution for last-mile connectivity of public transport in a multimodal transport system, and also the fact that these vehicles are electric mode of transport that guarantee the environmental concerns. These systems usually operate on a geo-fenced area, which means that the users have the flexibility to pick up and drop off the vehicle only within these defined geo-fenced areas. And the main challenge of this system is the matching of supply and demand. So supply and demand mismatch is the main challenge. From the supply side, operator need to consider the vehicle count or the availability of the vehicle. Due to uncertain demand during the day, and we have peak hours and off-peak hours, so the operator needs to have a prediction over this vehicle count. Most of the research focused on vehicle count only to optimize their rebalancing plan, and they often overlook the other aspects, which are the battery management plan, and another most neglected aspect is user behavior and user vehicle selection that would affect the system. In our research, we discretized the battery level into three classes: no power, low power, and high power vehicles. No power or inactive vehicles cannot offer service to the users, and they need to be scheduled for a battery swapping operation in order to enter the system again. And then the low power and high power can serve the demand, with the difference that low power vehicles can only address the average trip characteristics for an e-scooter, and they can cause range anxiety in the users. That we are going to capture these effects through a hybrid choice modeling that in the literature, and we are going to integrate all these three aspects and define the state of a geo-fenced area based on the perceived usability of the area rather than the vehicle count alone. So that's the main contribution of our research. Also, from the demand side, operators need to have a prediction over the demand fluctuation during the day, and as a consequence, the changes in the geo-fenced area state. For the actions of our rebalancing plan, we consider a hybrid actions that include both operator-based and user-based efforts and interventions. We have a truck which are owned by operator, and this truck has two compartments for carrying e-scooters and high-power batteries to do the loading and unloading and at the place battery swapping. And from the users, we only ask them to change their drop-off location to a neighboring zone in an exchange of an incentive, a fixed value of incentive. These actions are guided by a prediction model, a Markovian prediction model that anticipates the future loss of the system, the future demand loss of the system. This Markovian prediction model is powered by the behavior model and also consider the battery transition between these classes as well. The proposed framework is called direct look-ahead approximation because it explicitly simulates future outcomes through a model and integrates them directly into optimization decisions. We have a mixed integer linear programming optimization model that tries to optimize these actions. The proposed prediction model operates on expected state of the system, which means expected inventory and then the battery level of the system and expected demand loss. So we need to re-optimize the plan based on the real-time information. Whenever the information regarding the inventory of each geo-fenced area becomes available, we re-optimize our plan in a rolling horizon manner, which means that the future actions are discarded and the problem is re-optimized. To assess the performance of our proposed framework with the current state of practice and other rebalancing schemes, we used real data from a major European e-scooter operator that operates in a geo-fenced area in Rotterdam City, Netherlands, and we compared our framework with 3 other rebalancing plans. The first one is no rebalancing, which means that we have no intervention neither by user nor operator. The second one is only doing the relocating, which means the loading and unloading of e-scooter by the truck, which is the current practice of our case study. And the third one is doing the relocation and battery swapping by the truck. And then our proposed model, which means we are doing the loading and unloading and battery swapping by truck, as well as offering incentive to users. We also run sensitivity analysis to see the impact of passenger heterogeneity behavior toward vehicle selection and see the impact of this heterogeneity on the rebalancing plan. The result reveals that our plan enhances service level on average by 11% while managing operational costs compared to the current state of the practice. And also user-based relocation performs short-distance rebalancing that addresses local deficits. Within our method, the average kilometers traveled by truck per unit of served demand decreases, suggesting our method is environmentally more sustainable than truck-based policies. If you are interested in knowing more about the optimization model and more detail about the direct look-ahead framework, please feel free to scan the QR code and access the archived version of our research. Thank you for your attention.